time for us to do some practice involving curvature, which looks at the question of how twisted and bent our curve is. So this is a parameter. It's very similar to when we did the decomposition of acceleration, and we'll see that there's going to be very similar computations that come along the way. And as with before, a lot of it comes down to just being comfortable with the computations, which means doing practice. The more you practice, the more comfortable you get doing practice. This is one of those things where you can't just learn by watching. You got to get your hands dirty. So do as many problems as you can on your own. If you're following along, use the pause button. You see a problem? Pause. Try it out. See how you do. And then when you're ready to continue, unpause, and we can compare our answers. Well, let's begin. For our first problem, find the curvature, and curvature is denoted with this symbol kappa. It looks a lot like a K. So if you say K, between friends, we know what you mean. And our curve is sine, cosine, and half t squared. Now we're going to do this in two different ways. Now what are the two different ways to do curvature? Well, when you're in dimension 3, what you can say is that your curvature, kappa, is found by either taking r prime cross r double prime and dividing it by the magnitude of r prime cubed, or you can say, look, it's a sub n, whatever that is, divided by magnitude of r prime squared. So we're going to do both, and we should get the same answer both times, right? Well, if we do our job right, yes. So let's take a look. What do we need? Well, we definitely need to take r prime and r double prime. That's just unavoidable, no matter what. And it kind of makes sense, because if you want to know about how the curve is behaving, the r prime, that's giving us direction, and r double prime, that's acceleration, that's turning. That's a turning motion. So there should be a nice connection with our second derivative. So let's write those down. R prime is what? Well, take it entry by entry. Cosine, negative sine, and t. R double prime, negative sine, negative cosine, and 1. All right, so now we have our derivatives. Good, good. So let's start by the magnitude of r prime, because that shows up everywhere. So we're going to have to do that eventually. So the magnitude of r prime will be the square root of cosine squared and sine squared. Notice because we square, the negative goes away. So plus sine squared and then plus t squared. Okay, that's the square root of 1 plus t squared. Okay, that's not so bad. Now, let's go in our first variation. So our first variation says take a cross product. So we'll start by taking the cross product of r prime and r double prime. So what do we get? Well, we have r prime cross r double prime is I, j, k. You have to leave space because there's these functions we have to write down. Cosine t minus sine t, t minus sine t minus cosine t, 1. So if we work that out, let's see, I minus sine t 1, that's minus sine t I, j t minus sine t, so minus t sine t j, k cosine minus cosine, that's minus cosine squared k. Now going other direction, sine, sine, k, of course there's a minus and minus, but we're also subtracting because of the direction we're going, so that makes a minus sine squared k minus cosine t times I, that'll be minus t cosine t, but we subtract, so it becomes a plus t cosine t, and that's I, and finally I cosine tj, but of course we're subtracting, so that's minus cosine tj. So we end up with sine t, negative sine t, don't forget that negative, plus t cosine t, comma, minus t sine t, minus cosine t, comma, minus cosine squared minus sine squared. At least we have one good term. Minus 1. Good. Now, you can still do your dot product check. So in other words, if we take the dot product with one of these, it should be 0. So for example here, we'd have sine squared and minus t cosine t sine t. Here we'd have a plus t sine t cosine t, which gives us some cancellation. A plus cosine squared. We got a sine squared and a cosine squared. That gets us to 1. And minus 1 gets us to 0. And if you run up here, minus sine t cosine t. Here you'll get a t cosine squared t. There's a t sine squared t. We have t cosine squared, a t sine squared. That makes it t. Here you can get a plus sine t cosine t. But remember, we had a minus sine t cosine t, which cancels. And then you have a minus t, which cancels with the plus t we had before. So, all right. So, good. We did our cross product. Now, we're most of the way there. Except we have to do the magnitude. Okay, well, that's all right. We don't mind getting our hands a little bit messy with our algebra. I mean, it's algebra. It's going to be fun. So let's move it up a little bit, give ourselves some space, and let's see if we can figure this out. So the magnitude, r prime cross r double prime, will be the square root of, and now we have to square each term. So when we square the first term, well, it'll be sine squared t. The cross term will be minus 2t sine t cosine t, and then plus t squared cosine squared t. All right, so that's the first term squared. Going to add the second term squared. I'll add it right underneath. So the first term would be t squared sine squared. I'll put that here. T squared sine squared. The cross term will be a positive 2, so a plus 2t sine t cosine t, and then a plus a cosine squared t. And then at the end, a plus 1. Okay, good. So what happens? Well, if we lived a good, clean algebra life, as the saying goes, things should simplify, and they do. But it actually gets better than that. Notice you have sine squared and cosine squared. That makes 1. Here you have another sine squared and cosine squared. That makes 1 times t squared. Great. So when you put it all together, what do we end up with? Well, we end up with the square root of 2, because you have sine squared, cosine squared, and 1. Put that together is 2, plus, and then you have t squared. So we have our magnitude of r prime cross r double prime. We have our magnitude of r prime. We put it all together, and we get our answer. So we can say it's the following. It is the square root 2 plus t squared. That's our magnitude of r prime cross r double prime over the square root 1 plus t squared cubed. And that's it. We're done. Okay, now that's if we use this formula. What if we went this route? Well, let's go there and let's see where we end up. So to get there, how do we begin? We'll give ourselves some space here. We start with the magnitude of r prime. So remember how do you find a sub n? You start by saying, what is a sub t? So a sub t, that's the derivative of the magnitude of r prime. In our case, well, that would be 1/2, 1 plus t squared to the minus a half, because you can think of this as 1 plus t squared to the positive a half to begin with, times by 2t. Well, you can simplify. The 2's cancel out, so you end up with t over the square root of 1 plus t squared. All right, that's our a sub t. Now, the next thing is you say what? Well, we have that a sub n, quantity squared, is equal to the magnitude of r double prime squared minus a sub t squared. All right, well, we know these things. We can figure it out because we have r double prime, so we just take the magnitude of that. Well, it'll be sine squared plus cosine squared plus 1 squared. Okay, that's our magnitude of r double prime squared. Subtract, now we square that. T squared over 1 plus t squared. And if we look, what do we see here? Well, this is really 2. So we say, look, this first term here is 2. So this is going to become 2 times 1 plus t squared over 1 plus t squared minus t squared over 1 plus t squared. In other words, common denominator. And if we clean that up, well, that's 2 plus 2t squared minus t squared, or 2 plus t squared over 1 plus t squared. So that's a sub n squared. So we conclude, what is a sub n? Well, we take the square root. So we get the square root of 2 plus t squared divided by the square root of 1 plus t squared. And now, what do we see? Look, a sub n, you would take a sub n, which is this expression. So that would be the square root of 2 plus t squared over the square root of 1 plus t squared. That's our a sub n. And then divide by 1 over the magnitude of r prime squared. So 1 over the square, which is 1 plus t squared, right? Because it's a square root squared. And if you compare, they're the same, right? Square root of 2 plus t squared upstairs, good. And it's 1 plus t squared to the 3/2 downstairs, good. So the same answer. Now you might say, which one is easier? It depends. Sometimes one method is easier than the other. Oftentimes computing cross products can get a little bit messy, and especially if you do a cross product and then do a magnitude. But sometimes there's advantages. You just have to do the problem and then figure it out. All right, well, good. Glad we got the same answer both times. That's a promising sign that we did it right. So let's keep it going. All right, our next problem. Find the curvature, kappa of t, for r of t, which is t plus t squared, comma, t minus t squared, comma, 2t. And the question is, what's the maximum curvature that we obtain? In other words, just how bent does the curve become? So like the sharpest turn that we're making. Now, how sharp is that turn? So before we can answer the second question, of course, we have to answer the first question, which says, well, what's the curvature? All right, well, let's get into it. So we start by saying, let's find r prime and r double prime. We'll always have to find those anyways. And we'll always have to find the magnitude of r prime. So let's talk about r prime. That would be 1 plus 2t, 1 minus 2t, and 2. R double prime, well, that's really clean. 2 minus 2, 0. Wow, can't get much cleaner than that. All right, let's look at the magnitude of r prime. So the magnitude of r prime is the square root of, we'll have 1 plus 2t squared plus 1 minus 2t squared plus 2 squared. Well, that's going to be the square root of 1 plus 4t plus 4t squared plus 1 minus 4t plus 4t squared, and then plus 4. The 4t's cancel, and we're left with 1 plus 1 plus 4, which makes 6, and 4t squared plus 4t squared makes 8t squared, and that's as simple as we can get. All right. Now, you kind of have a choice, right? Because we talked about, well, you can do a cross product or you can find a sub n. Generally speaking, if your magnitude of r prime is like super, super clean, in other words, it's a perfect square, oftentimes finding the magnitude of a sub n is probably the faster route. But if it's not, then think about the other way. And in our case, look how simple r double prime is. So let's do this one by doing our cross product. So we proceed by doing a cross product, and let's see where we end up. So we're going to look at the magnitude. Well, before we look at the magnitude, let's actually find the cross product. So r prime cross r double prime, I, j, k, 1 plus 2t, 1 minus 2t, 2, 2 minus 2, 0. The more zeros you have, the better. Okay, so we get I, 1 minus 2t, 0. Nothing. See, that's why I said zeros are great. J times 2 is 4j. K times 1 plus 2t times minus 2, well, that'll be, okay, that's minus 2 minus 4t k. We'll write it like that, minus 2 minus 4t. Okay, good. Other direction. 1 minus 2t k, well, that would be subtract, and that'll be 2 minus 4t k, right? Because this is 2 minus 4t, but we have to subtract because of the direction we're going. Minus 2 times I, well, that would be minus 4i, but we subtract, so it becomes a plus 4i. 0 times something plus j makes 0j. Now, if you look, what happens? Something beautiful happens. We get a really beautiful cross product. We get 4, 4, and minus 4. That's it. We can even check this, right? Now, you might say, wait, well, how did this minus 4 happen? The minus 4t's cancel. It's a minus 2 and a minus 2. So you can check. You get 8 minus 8, 0. Good. 4 plus 8t, 4 minus 8t, the 8t's cancel, so you're up to 8, and minus 8, 0. So this has a really great cross product. So a sign we made a good choice. Now, if we want to find the magnitude of this, well, the magnitude of r prime cross r double prime, that's the magnitude of this vector for negative 4. Now notice, everything has a 4 in it. Pull it out in front. So what do we have? That's 4, 1, 1, minus 1. And so the 4 stays in front, and you get the square root of 1 plus 1 plus 1, because you square each one of those, which makes it 4 times the square root of 3. Okay, so there we go. That's our magnitude of r prime cross r double prime. So we're ready to write down our answer to the first part. The first part being, what's the curvature? So the answer to what's the curvature is the following. Kappa, which is what we use to represent curvature, which is magnitude of r prime cross r double prime over magnitude of r prime cubed, is 4 root 3 goes in the numerator, 4 root 3 divide by, here we're going to get 6 plus 8t squared to the 3/2 power. All right. And that's the first answer. What's our curvature? Now, there's a second part. What's the maximum curvature? Now, it sounds like there's going to be a hard optimization problem because it's like, oh, we got to figure out what's the right t that maximizes everything. Pull out some calculus tools. But we don't need that. Look, how many times does t show up? It's just there once. So if you stare at it and say, look, the only place where t shows up is right there, that t squared. And now we say to ourselves, okay, what's true? Well, the larger t squared is, the bigger your denominator is, meaning the smaller your expression is. So we should make t squared as small as possible. Well, how small can t squared be? The answer is the smallest it can be is 0. That's it. So we say, aha, we have an idea. So to maximize, we say choose t equals 0. And what do we see? Well, we get our kappa at 0 would be 4 square root of 3 divided by 6 to the power 3/2. Now we could leave it like that, or we can clean it up a little tiny bit. Not much, but what can we do? Well, look, this is really 4 square root of 3. Now, 6, I can think of that as 3 times 2. So I can think of it as 2 to the 3/2, 3 to the 3/2. And here's the thing. 3 to the 3/2, another way to write that is 3 square root of 3. 2 to the 3/2, another way to write that is 2 square root of 2. See, it's like 2, 2 to the half, 3, 3 to the half. And if you do it like this, you say, hey, look, The square root of 3's can cancel, and you can cancel a single 2. So you can write this as a 2 divided by, you didn't cancel this 3, and you didn't cancel that root 2. You can even, if you're somebody who really dislikes square roots in a denominator, there are people who really firmly believe that you should not have square roots in denominators. They're okay. I like them. I hang out with them sometimes. And what you can do is multiply top and bottom by square root of 2. And if you did that and cancel, you'll end up with a square root of 2 over 3. And there you go. That is the most bent. So in other words, if curvature is a measurement of how bent or twisted your curve is, the most bent happens at time 0, and the measurement of what it is square root of 2 over 3. All right, good, good. Well, on to more problems. Bigger and better, hopefully, right? Well, hopefully. Okay. Find the curvature for a circle of radius r. Now this gets back into our discussion. What is curvature measuring? And we said, look, curvature, it's trying to measure, like, imagine there's a circle involved. So the curvature of a circle should be something really, really beautiful, really, really clean. And that's our goal, is to say, hey, this is super, super clean. So that's where we're going. Now let's think about what our setting is. So right now our setting is we have a circle radius r, and we said, look, let's just put in our xy plane. So it's a two-dimensional thing right now. So we have our xy plane, and whenever we're parameterizing circles, the most natural way to do it is by the cosine sign. So cosine for the x-coordinate, sine for the y-coordinate. Except that's a unit circle. But it's easy to adjust. So if you scale the entries by r, that gets you to a circle radius r. So here we go, r cosine t, r sine t. That's our parameterization for a circle radius r. So here's our x, and here's our y. Now if we go back and look, we actually have a formula for how to do things in two dimensions when we have things like x of t, y of t. You can either rederive it, or you can look in your notes. I'm going to look in my notes, and I say, aha, in this case, we get the following. Kappa of t is, take the absolute value of x prime, y double prime, minus x double prime, y prime, divide that by the term x prime squared plus y prime squared to the 3/2. It's very quick to rederive this if you don't remember it. Just think of it as really saying you have x prime, y prime, 0. X, y, 0. And then you just go through and go. It's not so bad. But our point here isn't to derive this formula. Our point is, well, let's see what pops out. Because our goal is to say, is there really a circle connection? Let's figure it out. So if we think about it, well, let's think about our terms. So we have x is r cosine t, x prime minus r sine t, and x double prime is minus r cosine t. That's what we have. On the other hand, we get that y is r sine t, y prime, that's r cosine t, and y double prime is negative r sine t. So we get the following. X prime times y double prime. Well, you'll see, you'll get a positive r squared sine squared minus x double prime y prime. So we're going to subtract x double prime times y prime. So again, we're going to get an r squared, but there's a minus sign, so we're subtracting negative r squared cosine squared. Divide that by x prime squared, so that's r squared sine squared, plus y prime squared, r squared cosine squared to the 3/2. And now we're like, wow, this is so good. See, minus a minus makes a plus. So we have upstairs, it's really r squared. We don't need the absolute value, it doesn't do anything. Downstairs, we say, hey, sine squared cosine squared makes 1. It's really r squared to the 3/2, which makes it r cubed, which leaves us with 1 over r. And therefore, That's the curvature. Now notice what's not there. There's no t. None. There's no t involved anywhere in here. Well, what does that mean? Well, it means it doesn't matter where you look. So, in other words, the curvature over here matches the curvature over here, matches the curvature over there, right? They're all the same. And it makes sense because you say, look, there's that rotational symmetry. It shouldn't matter where we look. The curves all look identical. Any part of the circle looks like any other part of the circle. So it makes sense that there is no t. But now we also are able to more explicitly state, when we talked about how curvature looks like a circle, we say, aha. So in general, what this says, if you have a curve here, and you say, look, if I want to know what's happening with the curvature at a particular point, so if I'm saying, what's the curvature here? Well, the curvature says there's this circle that the curve looks like locally. Maybe that's the circle here. And this circle, which the curve locally looks like, has a radius of not kappa, not curvature, but rather 1 over the curvature. Because notice that here, the circle is radius r, the curvature is 1 over r. So when we talk about the connection between thinking about circles and curvature, that's our connection. So it makes sense, because if you think about, if we're having a quick bend, we're turning sharply, that should be a tiny, tiny circle. But we think of it as a large curvature, of course. So 1 over a large number makes a small number, so that's a small radius. Whereas if there's hardly any bend, that would be a huge radius. 1 over a small number makes a big number. So there we go. That's the more explicit connection. So now we can say what's going on a little more clearly. A little bit. All right, well, let's do a few more, right? We can do it. We've got the energy. Okay, on to our next problem. Ooh, all right. Find our curvature, kappa of t, for the following curve. R of t, root 2 over 2, t squared plus pi, t plus 1 e to the minus t, and t minus 1 e to the t. Okay, so that's what we're after. And we'll assume t is greater than or equal to 0. Now, there's no reason that t has to be greater than or equal to 0 at this point, but perhaps at some point in our computation we'll be like, oh, isn't it nice that our t is greater than or equal to 0? So something to look forward to. Well, let's get into it. Now, whenever we're looking for curvature, we should always start by focusing on things we're going to have to find regardless. R prime, R double prime, and dip our toes into the magnitude of R prime. Okay, so let's start with R prime and R double prime. So R prime, the nice thing, of course, the pi, which is the scary looking part, goes away. So the derivative, well, the 2 comes down, so we're left with root 2 times t. Now the next term, product rule. Root of the first times the second plus the first times the derivative of the second. And again, another product rule. So derivative of the first times the second plus the first times the derivative of the second. Now, it looks like we can probably simplify. So, for instance, let's take a look at our term. So, nothing to do in the first term. If we think of here, what do we see? We see an e to the minus t and a minus e to the minus t. Cancellation. Ah, beautiful. So what doesn't cancel? Well, this t and the minus e to the minus t, so that would be minus t e to the minus t. Here, there's an e to the t and a minus e to the t. More cancellation. What are we left with? Well, we're left with t e to the t. Okay, now that's r prime. What's r double prime? Well, that would be square root of 2. And then here, product rule again. So you get minus e to the minus t minus t minus e to the minus t. And then we get e to the t plus t times e to the t. Right? Derivative of the first times the second plus the first times the derivative of the second. We could even clean that up a little bit. What is that? That's square root of 2. And here, we're going to get, we'll get t minus 1, e to the minus t. And over here, we'll get t plus 1, e to the t. Okay, all right. Well, there we go. There we go. Now, let's turn to the magnitude of r prime. Oftentimes, the magnitude of r prime will give a hint about which way we should go in terms of how we solve the rest of the problem. So what is the magnitude of r prime? Well, that will be the square root of square each term. So here, that would be 2t squared. And here, well, that'll be a t squared e to the minus t squared. And there, we'll have a t squared and an e to the t squared. Notice that this minus, when you square it, goes away. And so there we have it. Now notice, all the terms have a t squared, so we can take the t squareds and pull them out in front of the square root symbol. And of course, the square root of t squared is t. Now, remember how we said, hey, at some point we'll probably use the fact that t is greater than or equal to 0. That's the point. Because normally the square root of t squared is actually the absolute value of t. So we're using the fact that we know that t is non-negative at this point to say, look, this is really t. And now we say, hey, we have 3 terms. When we have 3 terms, we start thinking, hey, you know, perfect squares have 3 terms. And the other thing we notice is think of the numbers, the coefficients, 2, 1, 1. And we're like, whoa, wait a second. If you take the 2, 1, 1 and rearrange it, it's 1, 2, 1. And that's how perfect squares often look like, with that 1, 2, 1 pattern. So it's like, we should be suspicious. Perhaps, they have given us a perfect square. Well, let's see if they have. Well, if they have, this 2 would go in the middle. So let's see. I like to be more optimistic. Let's put that e to the t squared at the front. Then there's a plus 2, and then there's an e to the minus t squared at the end. Now, if this were a perfect square, that would be our a squared, that would be our b squared. So our middle term would need to be our 2ab. So the question is, well, is this the same as 2 times e to the t times e to the minus t? And the answer is yes, because e to the t and e to the minus t, when you multiply them together, give 1. So we say, aha, this inside part is really e to the t plus e to the minus t squared, which means our magnitude of r prime is beautiful. And in particular, we end up with t times e to the t plus e to the minus t. All right, now, why is this important? Well, when we're thinking about which formula to use, we have to sort of make a decision. Do we think it's going to be easier to find a sub n, or will it probably be easier to do a cross product? Now, when is it easy to find a sub n, or at least easier? You know, we don't want to trivialize anything. There's going to be work here. But generally speaking, if your magnitude of r prime is clean and you get rid of a square root, it's a sign that it's not going to be so bad to find a sub n. So we say, okay, we have a plan. So our plan is we're going to say, look, we're going to say that our curvature, kappa, is a sub n over magnitude of r prime squared. So that's the direction we're going. Okay, so we need to get there. Okay, so we'll get there. All right, let's start by finding, first off, a sub t. If you want a sub n, the first thing is to find a sub t. So how do you do that? Well, a sub t, it's the derivative of the magnitude of r prime. Okay, well, product rule, derivative of the first would be 1. So you have e to the t plus e to the minus t plus, so derivative of the first times the second plus the first t times the derivative of the second, which would be e to the t subtract e to the minus t. Well, let's rewrite this a little bit. So let's group it by our exponential function. So there's e to the t has a t and a 1. So I'll write this as t plus 1 times e to the t. Now e to the minus t, there's a minus t there and a plus 1. I'm going to write this in sort of the following way. Minus t minus 1 e to the minus t. But you can check. It's all there, right? There's the minus t, e to the minus t, a plus 1 e to the minus t. And now we're like, whoa, look how promising this is. In particular, we're like, hey, that looks a little bit like that term. And this one here looks a little bit like that term. So we're just starting to go, promising, promising. All right, now we still have to do one more computation. And what's the last computation? Well, a sub n squared is you take magnitude of r double prime squared subtract a sub t squared. That comes back to our decomposition of acceleration. All right, magnitude of r double prime. So squared. We just have to take the square of each entry and add them up. So we're going to get 2 plus square of this entry, t minus 1 squared e to the minus t squared plus square of that entry, t plus 1 squared e to the t squared. Okay, that's the magnitude of r double prime squared. Now we're going to subtract this thing squared. Well, we have a subtraction here. So we're going to subtract. We'll square this one. T plus 1 squared e to the t squared. And so that's like our a squared. Then your minus 2ab. So minus, because of that minus, this times that. So that's t plus 1, t minus 1. And you're probably thinking, wait, you forgot the e to the t and the e minus t. But when you put those together, you get 1. So that's actually the middle term. And then, so that's a squared minus 2ab. If you like, we'll go ahead and just write the e to the t and e to the minus t and say, aha. But look, they cancel. Doom, doom. And then don't forget you have to have the b squared on the end. So plus t minus 1 squared and e to the minus t squared. Now, if we've lived a good, clean algebra life, beautiful things should happen. Let's see. Anything beautiful happen? Well, you have a t plus 1 squared times e to the t squared. And there's a t plus 1 squared e to the t squared. Pew, pew. They cancel out because of the minus. T minus 1 squared e to the minus t squared. T minus 1 squared e to the minus t squared. But remember, that one's being subtracted. So pew, pew. Wow, this is becoming great. What's left? Well, we have the 2. Okay, so that's there. And, oh, whoops. Do you see what I forgot? This is AB. There should be a 2 here, right? 2AB. So 2 minus minus makes a plus 2. And here, t plus 1 times t minus 1 makes that t squared minus 1. Well, really, there's a minus 2. There's a plus 2. That makes it 2t squared. All right, now that's our a sub n squared. Take your square root, and lo and behold, we can say, aha, a sub n is square root of 2t. So we put it all together, and what do we have? Well, we have our a sub n upstairs, square root of 2 times t, and then downstairs, what do we have? Well, we have t times e to the t plus e to the minus t squared. Now, we can do one more thing if we wanted to. Let's see. I don't know if we really have space, but, well, we'll squeeze it in down to this bottom corner down here. Notice you have a t squared, and then you have a t. So you could write it as the square root of 2 divide that by t times e to the t plus e to the minus t squared. And there you go. That's it. Wow, what an answer. What an answer. Maybe not the easiest or cleanest, but you can do it. There's a process. And just have to be patient and be really careful with your algebra. All right, good. Well, let's continue. We always want more. We're hungry for more. We've got a need to learn. So our next problem. Find the curvature at time t equals 0. For r of t is 71 plus log of t plus 1. And then there's tangent of t plus 2t squared plus square root of pi. And then there's e to the t cosine t minus e to the pi over 6. And you look at this and you're like, this looks crazy. And but maybe not. Maybe not. There's a couple of things. First off, some of these things don't really matter. Notice the square root of pi, e to the pi over 6. What are those? Well, they're constants. Well, what's the point? Well, what does the effect of adding those constants do? The answer is they're shifts. So it's like we're taking our curve and we're shifting it in space. Well, if you have some curve that has a bent shape and you shift it, it has the same bent shape. So in other words, curvature is unaffected by those pieces. And that's not surprising if we think about the formulas. Constants go away. So the square root of pi and e to the pi over 6, they're there to make us nervous, but we can see past that trick. No problem. No problem. What about the rest of it, though? Okay. Well, we still need to think about the rest of it. Oh, whoops. I forgot to mark the 71. That's also a constant. So the rest of it, well, you have bits and pieces, but they're all sorts of different functions, which means it's not looking too good for us right now. Let's talk about our various things that we need to do. Well, we need to compute the curvature, right? So curvature we have as what? Well, there's two ways to do it. You can do r prime cross r double prime divided by the magnitude of r prime cubed, or you could say, look, I'll find a sub n as a function of t and divide by the magnitude of r prime squared. Now, there is some good news on this problem, which should hopefully save us a lot of work. You see, we're not asked to find curvature for all times. We're asked to find it for one specific time. Now, why is that good news? Well, that means that we're going to have to evaluate. And so, when we have a problem where we have to evaluate, the question becomes, when do we evaluate? And the answer is almost always the following, is evaluate early. Now, what does that mean? If you have to evaluate, you want to evaluate as soon in the process as you can. Oftentimes people think, wait, don't I evaluate at the very end? Well, sometimes you have to, but other times you say, look, you can push the evaluation earlier into the problem, and the earlier you can push it in, what happens is you tend to collapse these large expressions into now numbers, making them easier to work with. So the question is, between these two options, which one will help us push our evaluation sooner? If you look at the first option, the one with the cross product, you'll see, look, as soon as I know r prime and r double prime, I'm good to go. I can evaluate, and then everything else, the cross product, the magnitudes, all that can be done after I plug in 0. So that's good. On the other hand, when I'm trying to compute a sub n of t, well, now we have to be careful, right? Because how do you do a sub n? Well, you first have to take the magnitude of r prime and then take the derivative. So you cannot just take r prime and evaluate. You have to keep the formula in all the way till post taking the derivative of the magnitude of r prime, which means you have to wait a while. So for us, we say, look, if we want to evaluate early, that's our approach. That's the one that lets us evaluate as soon as possible. So we're going to use that one. Okay, so here we go. What is R prime? Well, the root of 71 goes away. Like I said, 71 doesn't matter. It's a shift, no worries. Log of t plus 1, 1 over t plus 1. Derivative of tangent, secant squared. And then plus 4t. E to the t cosine t, product rule. Derivative of the first times the second plus the first, which is e to the t times derivative of the second. Derivative of cosine is negative sine. Okay, R double prime. And of course, imagine if we took the magnitude of that, it wouldn't simplify at all. And then we'd be like, and then we have to take the derivative. We'd be filling up pages. Oh, so uncomfortable, so uncomfortable. But we don't have to. So, R double prime. All right, derivative of 1 over t plus 1 squared is minus 1 over t plus 1 squared. Think of it as t plus 1 to the minus 1 power. So the minus 1 comes down, t plus 1 to the minus 2. Derivative of secant squared, well, 2 secant, and then the derivative of secant is secant tangent. And derivative of 4t, 4. And, okay, derivative of e to the t cosine t, that's e to the t, derivative of e to the t times cosine, and then e to the t times derivative of cosine, that's minus e to the t sine t. Here, subtract, then you have derivative of e to the t is e to the t, and then sine t stays the same. Then we're going to subtract. So this is subtract the derivative of the first times the second, e to the t sine t, and then first times the derivative of the second, so that's e to the t cosine t. Okay, good, good. Now, let's see what we have. Put everything together, and hopefully life is good, because we're ready to evaluate before we proceed. So, what is R prime of 0? Well, 1 over 0 plus 1, 1. Secant squared of 0 is 1. E to the 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. So it's 1. 1, 1, 1. That's great. Lovely to work with. A lot easier than that big expression. R double prime is 0? Well, what do we have? Minus 1. Here, secant of 0 times secant of 0 times tangent of 0. Well, tangent of 0 is 0. That goes away. So you have a 4. What do we have here? Well, notice the e to the t's, cosine t's cancel. That's nice. And now you see you have a minus 2 e to the t sine t, but we're plugging in t equals 0. So if sine of 0 is 0, meaning you get 0. Well, great. This is beautiful. Okay, how about r prime is 0? Cross r double prime is 0. All right, I, j, k, 1, 1, 1, minus 1, 4, 0. And we're going to get 0i. Then we're going to get minus j. And then we're going to get plus 4k. Then we're going to subtract minus 1k, so that becomes a plus k. And then we're going to subtract 4i and add 0j. So we're getting minus 4, minus 1, 5. All right, let's check. We should always check. Okay, minus 4, minus 1, plus 5. All right, that's 0. 4, minus 4, and 0. All right, that's 0. Good. Okay, so we're almost done. This is wonderful. Okay, so the magnitude, r prime is 0, cross r double prime is 0, over the magnitude of r prime is 0, cubed. So upstairs, that's the square root of 16 plus 1 plus 25. Downstairs, that's square root of 1 plus 1 plus 1 cubed. Now, we start thinking, okay, 16 plus 1 plus 25, what's the answer to that? Well, turns out it's a nice number. the number that's the answer to life, the universe, everything? 42. Okay, so it's the square root of 42. Now down here, you get the square root of 3 cubed. Well, that's really the square root of 3 times the square root of 3 times the square root of 3. Now it turns out that 42 is divisible by 1/3. So if you take 1 square root of 3 and divide into 42, you'd be left with the square root of 14. So that's one of the square root of 3's going into there. There's 2 square root of 3's left. So if you put those together, that gives you a 3. So you end up with the square root of 14 over 3. And that's not so bad. Notice that a lot of the computation was done just using numbers because we were able to evaluate early. This is a really good skill to have, to say, okay, I have a problem, but it's a problem asking for what's happening at a particular point. Let's try to evaluate as soon as possible. The sooner, the better. All right, good. Good rule of thumb. Well, let's continue. Okay, so our last problem. You find yourself on an adventure, traveling with 12 dwarfs to borrow Schmog's treasure. As you are crossing the misty mountains, your company finds itself being chased by goblins on a mountain path. From your vast experience of being chased by Farmer Maggot back in Hobbiton, you know that the best chance to evade capture is to hide by getting off the path at a point where the path sharply turns, because you want to, right? Because the more sharply it turns, that says, look, there's a bend. There's a chance for you to hide. Okay, so that means we're looking for a point with high curvature, and in particular, we want a point on the road where the curvature is above 10. Okay, so glancing at a map of the path, which you fortunately tucked away in your bag, you see that the path on the road can be parameterized by our lovely expression here. Okay, now a little known fact, Hobbiton prides itself on the multivariable calculus educations program. Yep, they're good. They're good. Now, Gloin, one of your dwarf companions, recommends getting off the path corresponding to the point where time t equals 2. Nori, another dwarf, thinks that the road does not bend sharply enough at that point, and instead they should only try to outrun the goblins. So which plan of action should you take? So, first off, there's a lot of text here. And you might be, I'm not sure what a dwarf is, or the Misty Mountains, or Schmog, or... Okay, even if you didn't know all of that, let's just think, what could we look for? When we're looking through a math problem, we say, let's look for math. And we say, hey, I see something like curvature. That's like a math thing, so we'll circle that. And I see, hey, there's this parameterization here. That's a math thing. And I say, oh, there's a time. And so we say, okay, so what needs to happen? Well, it says the question comes down to curvature. So is the curvature above 10 for this curve at that time? And depending upon whether the answer is yes or no, that's a jump off the path or keep running and hopefully that the goblins don't chase you any farther. In other words, this is a great application. In case you ever do find yourself being chased by goblins, now you know what to do. Just start doing some multivariable calculus. That'll really scare them. All right, well, the nice thing is we have a specific time. So, because we have a specific time, it's going to be easier if we just say, look, let's just evaluate at that time to see what happens. So, if we look at this as our curve, it's our curve, r of t. So our prime of t would be, taking the derivatives, 10t minus 20, comma, 3t squared minus 6t, comma, 6t minus 11. Our double prime, okay, derivative of each entry, 10. Here it would be 6t minus 6. And here it would be 6. Okay, it's not so bad. Now, we'll plug in time equals 2. So, r prime of 0, what do we get? Well, we get 20 minus 20. 0. Great. We like that. Now we have 12 minus 12. 0. Perfect. And here we get 12 minus 11. Oh, that's not so bad. That's 1. So that says the magnitude of r prime of 0 is equal to 1. Wow. Wow, that's fantastic. That's going to make our denominator really, really simple. So we just need our numerator. Well, the way we're going to do that is we also need to know r double prime is 0. Well, sorry, not r double prime, r prime is 0, r prime of 2. R double prime of 2. Sorry, time equals 2. So often we do problems where time is 0. Bad habits to just sort of, oftentimes you get into sort of a manual mode and forget, wait a second, don't. You gotta pay attention. Okay, 10, 12 minus 6 is 6, and then 6. So we are not done yet because we need to find r prime cross r double prime. Well, that would be ijk 0, 0, 1 and 10, 6, 6. Now, the good news is you got a bunch of zeros. The more zeros you have, the faster the computation goes. Watch. I times 0 times 6, 0. J times 1 times 10, 10j. K times 0 times 6, 0. 10 times 0 times k, 0. 6 times 1 times I, that's minus 6i. And 6 times 0 times j, 0. So what do we have? Well, we have minus 6, because that's the I, and then plus 10, and then 0. So to finish off, we say, look, our curvature at time 2 is equal to our magnitude of r prime of 2 cross r double prime of 2 divided by the magnitude of r prime of 2 cubed. Well, the denominator is 1. Done. Upstairs, what do we have? Well, that's going to be the square root of 36 plus 100. All right, that's the square root of 136. Now, what do we need? We need to compare it to 10. Is the square root of 136 above 10? Yeah, it is. It is above 10. And so we say, perfect. This is bigger than 10. So it means that at that point, time equals 2, it's turning pretty well. In fact, there's a good chunk of turning here. So that means that we do have a nice turn. Now let's figure out. So Gloin, he said we should get off the path, and Nori said we should keep going. Well, because it has that high curvature, that's a point of escape. So our answer, whose plan of action should we take, is we should go with Gloin. Gloin will get us off and help us escape from danger. All right, well, another wonderful way that calculus can be used to help us in real-world applications. All right, good. Well, thanks for coming, and I hope to see you again. Bye.